Okay, welcome my dear students. In the last class, I just explained you about the matrix T related to the basis B, ordered basis B and C, and we proved that one result. That means matrix of a T related ordered basis vector of a any if we have a T from V to W is a linear transformation, and then B and C we have a are the basis, ordered basis are there. Then T of V related to the basis C can be written as a matrix related to the basis B and C and the coordinate vector of a VB. So that means this T we can say that any linear transformation can be written in the form of a matrix into the coordinate vectors of the this corresponding to the basis B. Okay, so now in this class we discuss about some examples how to find a matrix related to the basis standard given ordered basis are there. Okay, just start with the very simple example. We can say that T from R3 to R3 defined by this. I take a B is the standard basis, E1, E2, E3. Then first we find what is the coordinate vector of this corresponding to this basis. So we can say that X, Y, Z are the elements of a R3. Then this we can say that this X, Y, Z can be written in the form of finite linear combination of the elements of this. So alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3, and this can be written in the form of alpha 1 we have a 1 0 0 plus alpha 2 0 1 0 plus alpha 3 we have a 0 0 1, and now this can be written as alpha 1 we have a alpha 2 we have a alpha 3, and this giving you have a alpha 1 is equal to X, alpha 2 is equal to Y, alpha 3 is equal to you have a Z. So this means we can say that if we take this corresponding to the this we have a coordinate vector V with B is equal to nothing but is equal to, you can say that we have a X Y Z. So we can say that this is X Y Z, and then we have to similarly we calculate the T is giving to this, then ordered basis of this. So we have to calculate T of E1. T of E1 is equal to, you have a 1 0 0. Now we have calculate T of E2. E2 is equal to 0 1 0. Now calculate T of E3. T of E3 is equal to, you have a 0 0 1. Then corresponding to the basis we can say that C, T of E1, I take a coordinate vector of a T of E1 corresponding to the basis we have a B, because we have R3 to R3, both the bases are the same. So this is the nothing but is the column vector of you have a 1 0 0, and then we can say that corresponding to the T of E2 corresponding to the basis B is equal to, we have a column vector is equal to 0 1 0, and now we have a T of E3 corresponding to the basis B is equal to column vector you have a 0 0 1. Now I just said that we can say that T of V, and now this is the corresponding to the basis B or C. This is the same thing. So corresponding T of V can be written in the form, I just said that this T of we can say that V in general, V can be written as a T of BC. C is equal to, you have it, I just write it a B, this is equal to B, this is B, this is B, and you have a coordinate vector of a B. Then we can say that this is nothing but is equal to, write in the matrix form, you have 1 0 0 0 1 0 0 0 1, and this is nothing but is equal to, we can say that write in the form of a coordinate vector is X Y Z. Now you to verify that this is nothing but is equal to, in this form you can just say write into this sorry, this is E2 is equal to is a minus, sorry, this is E2 is equal to minus, so this should be a minus, this should be I have make a mistake, this should be a minus here. So this means we can say that this clearly you have a X, you have a minus Y and Z. So T of representation of this linear transformation, this linear transformation can be represented in the form of a matrix. So there exists a matrix 1 0 0 0 minus 1 0 0 0 0 sorry 0 0 1, and then if we multiply this is the x1 x my x and coordinate vector of a this R3 with respect to this. So we can represent that this is a matrix, and this matrix product can represent this whole linear transformation can be represented by this matrix. Okay, so now we just say that if we have a ordered basis higher here, so this is a T of B, T of B or C, whatever this you can say, we calculate into this form. Okay, so this means this is the coordinate vector. Suppose we have to assuming that V is equal to 1, 2, 2. So this is the coordinate vector of this. Then we calculate the T of BV is equal to, we have this. And now if you have a, this is the vector V. Now we have a defined in the form, if you take X, Y, Z, we have defined in the form of X minus Y into Z. Now if you calculate T of V, the T of V means you have a 1, 1, 2, we calculate this is equal to 1, minus 1 and 2, this is the same, we have to representing this. So any coordinate vector, if suppose we have a coordinate vector is equal to 2, minus 3 and 0, then this V of a corresponding to B is nothing but is equal to 2 minus 3, 0, because we have a standard basis. So this means we can say that 2 minus 3, 0 can be written as a 2 times of a E1 plus minus 3 times of a E2 plus 0 times of E3. So this is the column vectors, 2 minus 3 is this. And now if we calculating this T here, so this is the matrix we have a corresponding to the this standard basis is equal to this. So we can say that T of V corresponding to the basis V is equal to, you have a matrix 1, 0, 0, 0, minus 1, 0, 0, 0, 1, and the coordinate vector we have a 2 minus 3 and 0, and this is nothing but is equal to, you can say that this is equal to, you have a 2 and then you have a 3 and then you have a 0 and 2, 3, 0 is this matrix representation of a this, if we take a different coordinate vector. So in this way we have to change a different coordinate vector. We can define this matrix is already there by corresponding to this standard ordered basis, then we can find the linear transformation this one. Okay, so now we move to another example related to the polynomials. I just take again the basis into this form. So this is the basis for B. If this vectors can be is a basis of this, any vectors of T of V corresponding to the B is nothing but is equal to, we can write as a, because of the basis of this trivially. So this is 1x, x square, x cube. So this because these are the standard basis. So any polynomials we take a0, a1x, a2x square, a3x cube can be written in the form of a linear combination of this. So alpha 1 into 1 plus alpha 2 into x plus alpha 3 into x square, alpha 4 into x to the power 4, alpha 1 is equal to, you have a a0, alpha 2 is equal to, you have a1, and then you have a, and similarly all these things you can just say that. So this means you can simply say that any constant can be written as a coordinate vectors of this. So now we have to calculate this first. So T of we have to calculate it 1, and now you have a T of fx is defined in the form of a derivative of this. So T of 1 is equal to, we can take a derivative of 1 is equal to 0. This can be written as a 0 plus 0 into x plus 0 into x square. Now we have to calculate T of x. T of x is nothing but is equal to 1. This can be written as 1 plus 0 into x, 0 into x square. Now we have a T of x square. We can write it as a 2 of x. 2 of x can be written 0 plus 2 into x plus 0 into x square. Now T of x cube. This can be written as a 3 times of x square. This can be written as 0 plus 0 into x plus 3 into x square. So this means all this we calculated, and now we have to just say that T of 1 corresponding to the basis C is a column vector 0, 0, 0, and now we have a T of x corresponding to the column vector C is equal to 1, 0, 0, and now T of x square corresponding to the basis vector is equal to, you have a 0, 2, 0, and now T of you have a x cube corresponding to the basis C, you have a 0, 0, 3, and then we can say that T of V corresponding to the B and C can be written in the form of a, we have a 0, 0, 0, 1, 0, 0, okay, 1, 0, 0, then we have a 0, 2, 0, then we have a 0, 0, 3, this is a T, and now if we have any matrix defined into a this form, can be calculated into this form. So this is the this way we can calculate into this form. So this we can say that I take a T0, 0, I already explained you this, 2x then x cube. So this means T of relative to the basis is into a this form. So this way we can calculate into this form. Now we have to important remark is this matrix representation and choice of a basis. The matrix representation of a linear transformation depend upon the choice of a basis for the vector space involved. Why I say that is these things, if you remember, I just say that this is like a T of is the first example we have to just discuss about here. We have R3 to R3, we have a x, y and s, y, this. So we have to just take why I say that is involving, this means we have a x, y, z we define as the form of a x minus y and z. Suppose we take a basis of a R3 is B is not a standard basis, we take a some basis is equal to 1, 0, 0, 1, 1, 0, and then we have a 0, 1, 1. These are the bases clearly, and if we have to calculate this into the corresponding to this basis, you have to just take a if we take a x, y, z can be written in the form of a alpha times of a 1, 0, 0 plus beta times of a 1, alpha 1, alpha 2 we can just take alpha 2, 1, 1, 0 plus alpha 3 you have a 0, 1, 1. Then you have a alpha 1 plus alpha 2 is equal to x, then you have a alpha 2 plus alpha 3 is equal to y, then you have a alpha 3 is equal to z, then you have a alpha 2 is equal to y minus z, then you have a alpha 1 is equal to x minus y plus z. So this means we can say that we substitute here, so we getting this is equal to, we can write alpha 1 you have a simply is equal to x minus y minus z, can be written as a 1, 0, 0, plus you have to write this can be alpha 2 can be written in the form of a, you have a this y minus z, then we say this can be written as a 1, 1, 0, plus you have to write is a alpha 3 is equal to, you have a z can be written as a 0, 1, 1, and then we have a this any arbitrary vector for this we have to choosing this is a coordinate vector of this. For example, if we take a t, so t of x, y, z is defined into a corresponding to the this basis, we have to take a this different way. So this linear combination, this means is in this form. So this means clearly this is a form of a sorry, this is a y, and then if we change the basis, then completely matrix is also changed. So this way we can just say that if we have to calculate the basis of a corresponding to t of is this form, and now we have to calculate t of, we have to, for example, t of we have a 1, 0, 0, you have a simply is a vector in the form of a, you have a 1, 0, 0, and this 1, 0, 0 can be written in the form of a simply is equal to 1 into 1, 0, 0 plus 0 into 0, 1, 1, 0 plus 0 into 1, 1, and then this is corresponding to the t of first coordinate is equal to 1, 0, 0, 0, corresponding to the basis b is equal to column vector 1, 0, 0. And now if you take a corresponding to the another, so we have a t is equal to, you have a basis 1, 1, 0, this can be written as a, you have a 1 minus 1, 0. So this can be, you can write as the form of a this is the form of a, this thing you have to write is equal to 1, 1, 0, sorry 1, 0, 0. So this vector can be written in the form of a, we have to write 1 minus 1 0 can be written in the form of a we write in the form of a this thing is equal to, we need a 1 minus 1, so we just say that is equal to, we can say that is equal to here is a 1, this should be equal to, clearly this should be is equal to, if we take this is equal to 0, this is a minus 1, and then we have to take is equal to 2, so this is equal to 2 times 1 0 0, plus you take a minus 1 times you have a 1 1 0, and plus you have a 0 times 0 1 1, and then you can say that 2 minus 1 is equal to, you have a 1, and then 0 is minus 1, and then you have a 0. So this represent into this form. So if this is corresponding to this, we can say that the matrix of this corresponding, I just say that we can take into this form. So corresponding to this, what we have the matrix written in the form. So T of, we have to just take a 1 1 0 corresponding to the basis B is written in the form of a, you have a 2 minus 1 0, and in the similar fashion we have to calculate T of 0 1 1, and then T of 0 1 1 is equal to 0 minus 1 and 1, and then again you have to just take this, so you have a 0 times this, and then we have to taking is equal to this should be a minus 1 into here, so this is equal to, we have to take a 2 times of a like this, 1 minus 1 times of a this, and plus 2 times of a this, so again different matrix. So this means what is the meaning of this? Simply is meaning of this, the matrix representation of a linear transformation depends on the choice of a basis for the vector space involved here. Okay, so even if we keep the same basis vectors but change their order, the entries of a matrix will change. Okay, so this means we can say that the previous example, I just say that I take a example like this, I change the order of this, then we have a 0, and then we have a 1 0 0, and now a 0 1 1. I take a basis this, here you can just say check this way, I take a second one is equal to column is equal to, this is the matrix is this form 1 0 0, then is equal to 2 minus 1, and then one more vectors higher we corresponding to the this. But if you see, if we calculating corresponding to this means order of is the same. So this means the matrix representation, this order of a basis of the is choice in representation of a matrix depend upon the choice of the basis is in plex, even if their order is very important. So when we calculating the linear transformation, corresponding matrix related to the basis B as ordered basis. That means ordered basis is very important when we have to calculating the matrix representation of a linear transformation. Okay, now second thing is both the basis and the order of its vectors determined by a specific matrix of the transformation. So that means by these two we can say that both the basis and order of its vectors determine the specific form of the matrix. Means if we change the order of a basis, we can change the matrix also. Similarly, if we have to matrix representation, if we have a choice of the basis, if we have an identity basis, we have a one set of a matrix representation. If we have a change the basis, the matrix representation is changed. So means every time we have to change the basis, because you know that basis there is a various choice of a basis. There is a we have a keep a basis is not the unique, so we can find the different basis over there. So that means choice of the basis is very important when we have to calculating the matrix representation of a linear transformation. Okay, so now the second thing is the zero transformation. What is about, we can say that about the zero transformation. The zero transformation always correspond to the zero matrix regardless the basis, since every vector maps to the zero vector. Why? Because you can say that whatever basis we have to choosing is this doesn't matter. Why? Because we have to T is a map from V to W. We have to, and the map if defined of T of V is equal to 0 for all V belongs to V. Whatever choice of a basis is, doesn't depend. We have to always whatever we have to calculating is this T of V corresponding to the basis B is always we getting the T000 form like this. So this means we can say that for example, if you want, I just take one example from R3. So we take a T from R3 to R3, that the previous map defines the similar x, y, z is mapped to the 0, 0, 0. Then we have a basis is equal to, we have a E1, E2, E3. Then we have to calculate of a T1 is equal to, you have a 0, 0, 0, and T of E2 we have to calculating. This can be written in the form of a, we can, because is the 0, 0, so this can be written as 0 into E1 plus 0 into E2 plus 0 into E3. T of E2 also can written as 0 into E1, 0 E2 plus 0 into E3, and T of E3 can also written in the form of a E1, 0 into E2, 0 into E3, and that means we can say that corresponding to the T of E1 basis is equal to, we have a 0, 0, 0, then T of E2 corresponding to the basis we can say that 0, 0, 0, then T of E3 we have a B is equal to, we have a 0, 0, 0, then we can say that T corresponding to the B over B is the same as the 0, 0, 0, 0, 0, 0, 0, 0, 0. So that means whatever choice of a, if we have a zero transformation, then whatever the choice of a basis is regarding less. So this means every time we have to getting is a zero matrix. So this means this we have a getting in the general. So every entry in this matrix is 0. This matrix is called the zero matrix for all of order m by n, and it is denoted by 0 by 0 m is this. Okay, now we check what about the identity matrix. If we have a identity matrix, that means we have a always defined from U to U. That means basis is equal to B and C is the same. We have a basis is the same. So I take a identity matrix. So we can just try again with the example. So again take a R3 to, I take a R3, and then V is equal to, we take a some standard basis E1, E2, E3. Okay, so if we take a standard basis, then we have to define a map from x, y, z is the same as a x, y, z. And now we have to calculate a T of E1 is equal to, you have a clearly is equal to, you have a 1, 0, 0. This can be written 1 into E1 plus 0 into E2 plus 0 into E3. Now T of E2 we calculate in the form 0, 1, 0. This can be written as a 0 into E1, 0 into E1 plus 1 into E2, 0 into E3. Now T of E3 we define the form of a 0, 0, 1. This can be written in the form of a 0 into E1, 0 into E2 plus 1 into E3. So this means we just say that from this, the corresponding to T of E1 with the basis B is equal to, you have a column vector 1, 0, 0. Now this is a T of E2 corresponding to the basis is equal to, you have a 0, 1, 0. Now corresponding to the E3, this is equal to B. We can say that we have a 0, 0, 1. And then clearly we can say that T is corresponding to the basis B over B. We can say that is nothing but the matrix 0, 0, 0, 1, 0, 0, 0, 1. In the case of we have a identity matrix. But if we change the matrix, identity matrix to any other matrix, so we have a like this. So this is means we have to, if we have a relative to basis B, then we have the matrix called identity matrix denoted by a simply n is understood. Suppose we take a not the you transform, we take some basis, some different basis like this. So B I take the form of a 1, 1, 0, then we have a 0, 1, 0, then we have a 0, 1, 1. Then clearly we have these are the vector basis. If this is basis, we can calculate. This is again R3 is R3. T of 1, 1, 0 is the same as a 1, 1, 0, and then we can write the alpha times of a this is equal to 1, 1, 0 plus alpha 1, alpha 2 times of a 0, 1, 0 plus alpha 3 times we have a 0, 1, 1. So this means that alpha 1 is equal to, you have a 1. Now you have a alpha 1 plus alpha 2 plus alpha 3 is equal to 1. Now you have a alpha 3 is equal to 0. So you have a alpha 2 is equal to, you have a again 0. So this means we can say that alpha 1 plus alpha 2 is equal to 0. So this means we can say that T of corresponding to this is equal to basis is equal to first basis is equal to 1, 1, 0. We can say that this can be written in the form of a corresponding to the basis B is equal to one of the column is equal to 1, 0, 0. Now try to find the second we have to just try. We have a, what is a 0, 1, 0. This is again is a 0, 1, 0. So by this we can say that alpha 1 is equal to 0. Then we have a alpha 1 plus alpha 2 plus alpha 3 is equal to, you have a 1. Alpha 3 is equal to, you have a 0, implies that alpha 2 is equal to 1. So we can say that T of matrix corresponding to, you have a 0, 1, 0. If B is equal to, you have a again vector 0, 1, 0. And now we try to form the another. If we have a T of 0, 1, 1, and then we can say that this can be written as a 0, 1, 1, and this can be written in the form of again by this alpha 1 is equal to 0. Now you have a alpha 1 plus alpha 2 plus alpha 3 is equal to 1. Alpha 3 is equal to 1. Alpha 3 is equal to 1. So this implies that alpha 2 is equal to 0. So we have to just say that T of, we have a corresponding to the basis is equal to 0, 1, 1, and then corresponding to the basis B is equal to, you have a column vector is equal to 0, 0, 1, and then again you see this, we can say that T with related to the basis B over B is same as a 1, 0, 0, 0, 1, 0, 0, 0, 1. So what we show that whatever we have to change the basis, but this means this always we getting the identity matrix. If we have a identity transformation, then we can say that simply is equal to we take a two different example. First we take a standard basis is giving the identity matrix, of course. If we take a different basis set of a basis, then we also check, and then after checking this we can find that this again give it the same identity basis. So this means if different bases are used, the matrix representation, the identity transformation may or may not be the standard identity matrix. This is the question we have to just taking is this, but is not the standard identity form. That means we have to some identity matrix is a change. For example, this I just take this example. We have a 1, 1, 0, and we have a 0, 0, 1. This is a previous example. I want to check is this. I change the order of this matrix here. So I just take a 1, 1, 0 and 0, 1, 1. So I take a element of a 1, 1, 1, 1. I take a 1, 1, 0. Sorry, 0, and then I take a 0, 1, 1, and then we have a 0, 1, 0. Now I'll just check. You have a already calculating. This means you have a basis like this. T of 1, 1, 0. We already calculate for this. B is in the form of you have a 1, 0, 0, and then T of we have already calculated 0, 1, 1 for this corresponding coordinate vector of this is equal to 0, 0, 1, and then we have to calculating the T of 0, 1, 0, and this is corresponding with the coordinate vector is equal to 0, 1, 0. Then in this case we have a T of B2. B is nothing but is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1, and 0, 1, 0. That's why I am saying that. Always you getting this in this form is this, but identity matrix, if you take a different basis, I take a same basis, but I change the order of a basis, then we get a matrix is different matrices there. That's why I am saying that when we calculating the matrix transformation, basis of order of the basis is very important. I choose a same basis and I take an identity matrix, but one of times is matrix is this form, and the previous one we have to say that we have to calculating the only the standard identity matrices, but that is not a standard identity matrix. If we have to change the order of, again this is this, suppose B I can write in the form of this. I take a 0 1 0 basis vector, then you have I take a 0 1 1 and then 1 1 0. Then you can say that in this case you have a T B is the form of corresponding to the last one, you have a 0 1 0, and corresponding to the this one you have to just say that already you have to calculating is equal to 0 0 1, and corresponding to the this we have to already calculate 1 1 0. Now I have to change the order of the basis, then every time I change the order of a basis we getting a different matrix. So this is the very important note. We can say that means if different bases are used, the matrix representation of the identity transformation may not be the standard identity. This is the standard identity, but this is not the standard identity. This also is not the standard identity. So that means clearly we can say that if we have to using the identity different basis, we can just set in the identity. But if we have to say this, if we have to taking the form when the transformation is identity map, then whatever basis we have to choosing, the elements are like this, the 1 0 0 0 1 0 0 is the form of this, but maybe not in the standard form of the basis. Okay, so now I just I have to stop today's class here. In the next class we discuss about the find the linear transformation of matrix linear transformation of a sum of a two linear maps, or the composition of a two linear map, how we calculate the linear transformation of sum of a two linear maps, or skew composition of a two linear map. So we discuss into the next class. We have to prove a theorem also, linear combination of a linear matrix transformation of S plus T is the same as a transformation of a S plus transformation of a T. And also if we have a alpha times is some scalar, alpha time T is equal to alpha times of a matrix transformation of a T. Okay, so we discuss this all this into the next class. So thank you very much for this class. Continue into next class.